All right, so today we're going to continue on what we've been working on, searching and sorting. Just make sure, absolutely sure that this works here. Anyway, we left it off last time. We were talking about binary search, and we did a full implementation, but it was a recursive implementation here. So what I want to do now is I want to review how we went about doing this implementation. And then I want to change it so that it is not a recursive implementation. Remember, recursion in general is kind of bad because you might be doing duplicate work. That's not going to be the case. Oh, I guess, yeah, is that I would do that. It's not going to be the case with this particular problem, but you're still paying for the recursion. You're still paying for all those function calls. So if you can take the same thing and do it non-recursively with just a regular old loop, that's even better, okay? So again, the idea of binary search is that you suppose that it's sorted, and you can exploit that structure. The way that you exploit that structure is by looking in the middle. And if that's the thing that you're looking for, then you're done. Otherwise, what you have one of two options, right? The thing that you're looking for is less, and so you explore this side of the array. The thing that you're looking for is greater, and you can explore this side of the array. In either case, you've cut it in half each and every single time. This is a basic divide and conquer strategy. All we're going to do now is we're going to implement binary search, but in a non-recursive way, okay? So I'm going to go, oops, sorry. I'll go ahead and cut and paste this prototype right here. And you're going to help me with this, all right? I'm going to rename this one recursive because, of course, I can't have two functions with the same name here. And you're going to help me out now. Now, instead of passing in a left and right, what I'm going to do is I'm going to keep track of those as local variables. One of them is going to start at one end, the other is going to start at the other end, and they're going to move in, move in, move in, move in until they've gone past each other. Now, in the original recursive version, once they went past each other, that was our base case, in which case we returned from the recursion and we didn't do any more recursion, and it was an unsuccessful search. We used the flag value -1 to indicate that we didn't find what you were looking for, right? So let's go ahead and establish those two variables locally instead of passing them in. Int left is equal to something, right? And int right is equal to something, right? Now, because those somethings are there, I no longer need them as part of the input. What do I need now, though, as part of the input? Where do I start my left? At 0, right? Where do I start my right? The length of the array, the size of the array, -1 at the last element. So in general, that's going to be used, we're going to use the variable n to do that, but that means that I need to be passing it in now, right? There. So I've got my left and my right, and while the left is less than or equal to the right here, I need to examine the middle element and move these left until they meet in the middle, in which case I still want to check that one element to see if that's the thing that I'm looking for. But once they go past, that's when I'm done with the search and I say that it's an unsuccessful search. How many times am I going to be doing this? I could get lucky on the first one and say, oh, you found what you were looking for right there, right? So ultimately, I could be doing this, I think we went over it last time, log n times. Sometimes I get lucky, though, and I get immediately stopped. What kind of a loop do we want to establish here? Because I don't know up front how many iterations it's going to be. A while loop, all right? While the left is less than or equal to the right index. Yeah, go ahead.
So why is it in C that we pass in the size of the array, but in Java we don't?
Because in Java, it's part of the array. If you have an array in Java, dot length, that's built into the language, and you don't need to pass it in. Or if it's a list, then dot size, and that's our actual function call, that tells you how big the array is. C, older language that was not built in, right? There is a cost to that in Java. There's some additional overhead to keep track of that metadata. But in C, Nope, it can be anything. In fact, it can. This is just a generic. This is just a pointer. You can expand that memory using realloc or some other function calls to expand that memory or contract that memory, so it doesn't even have a fixed size. But in Java, once you've created an array, that's it. That's as big as it can be, forever. Right? You want something larger, you need to create a new array to do it. Right? So while the left is still less than or equal to the right, we move in. After we break out of this loop, though, we know that it was an unsuccessful search, and that's our base case there. Right? Why should I use const int? Good question. Why are we using const here? Am I going to be making changes to the array? Nope, I'm just searching for the needle in the haystack. I don't want to mess up the haystack, right? Any more than it already is, right? So I'm not going to be making changes to it, and const ensures that I'm not going to be making changes to it. Good question from YouTube, right? Okay, so while left is less than or equal to right, all I'm going to do is the exact same stuff as up here. Now, remember that this is bad in practice because this is susceptible to overflow. Think about, say, 2.147 billion and negative 2.147 billion, and if you take the 2.147 billion, 2.147 billion, you add those together, right? That's overflow. That'll be a negative value. Divide by 2 is still going to be a negative value. Is a negative value a valid index? No. So be careful with this. Don't do this in practice. In practice, though, you don't even write your own algorithms like this. In practice, you use what's in the libraries, and we'll show. That's where we'll go next after this. Okay. Otherwise, if the thing that you're looking for, a sub m, I called it a instead of array, is equal to the key value that you're searching, I will return the index at which I found it, m. Right? M is an index here. Okay. Else if the thing that you're searching for, the key value is less than that middle element, then you need to search where? In the left or the right? The thing you're searching for, here's m. The thing you're searching for is less, so I go left. Right. Else, if, and then the key value a sub m is greater than the thing that you the thing that you're searching for is greater than the middle element, then you need to search into the left or the right. Excuse me. Search right. Now, how do we do that? When I made this function call over here, when I made this recursive call, I just simply updated the left or the right index. Right? If you're searching to the right, right, then you updated the left index. If you were searching to the left, then you updated the left index. And that's what I'm going to do here. If I search left, which one should I update here? Search left index. So I'm going to update the right index to be m minus 1. If I search right, it's going to be left is equal to m plus 1. Oh, sorry, 1. There we go. All right. That looks almost exactly what we've done up here. If we search left, then we update the right index to be m minus 1. If we search right, then we update the left index to be m plus 1. Right? So we've taken this recursive version of it and we've unraveled it so that it is only a simple while loop here. We're no longer abusing the stack space. We get the same output. We get the same output and all that stuff. Line 65 is negative, less than. I think it should be greater than. 65 right here. So I did switch around the key and the middle element here. So I wanted to make sure that the key was over here. If the thing that you're searching for is greater than the middle element, then we're good. Right? Granted, if I put key first, then I would want to reverse those. You can write it either way that you want. That was a comment from YouTube. Let's go ahead and make sure that this actually works. To do that, I'm going to have to put in binary search recursive. There we go. And I'm going to have to put in the prototype here as well. And let's come over here and actually call our function now. The original here was recursive. Now we're going to call our regular binary search with just the size of the array and the key that we're looking for. Now, if everything's correct, then we should be searching for 42, and all three of these answers should come out to be the same thing. Search.c and demo.c. Oops. Darn it. No, I did not mean linear search. Oh, sorry, I screwed up. When I renamed the recursive version, I needed to rename the recursive calls as well. There we go. And now it should run 777. If you search for something that doesn't exist, 421. -1, -1, -1. I didn't find it. I didn't find it. I didn't find it. Right? Remember why I had to pre-sort this? Did it work when it was sorted? When it was not sorted, excuse me? Nope. Why didn't it work when it was not sorted? Oops, well, 421, it's not 42. There we go. I'll restore that. A successful search. Linear search finds it at index 0. But the other two don't find it at all. Why? It looks at the middle element, and it assumes that it's sorted. And if you're searching for 42, that middle element was, what, say, 9? And it ends up going in the wrong direction. It assumes that it's sorted, so 42 must be over here. But it's not. It's actually over there. So there is a cost to, or there is an assumption here to binary search that it has to be sorted to begin with. So let's start talking about that. How do we sort stuff? Oh, come on. There we go. Let me go ahead and give you that same example array that we were playing with. All right. Help me sort it. What's the first step? What would you do? No? Yeah, go ahead.
Put the, so see if the 40, don't give anything at 42, but then if 4 is bigger than 42, put it.
Oh, okay. So look at the first two and see that these are out of order. Go ahead and swap them.
Go ahead and swap them.
Okay. That would lead to 4, 42, 9, 4, dot, 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 dot. Then what? Same thing with what?
The next one, 42 and 9.
42 and 9? Okay. So are those in order or out of order? Out of order, so we swap them. And we have 4, 9, 42, 4, 102, dot, dot, dot. Now what? Keep going, right? Keep going, keep going, keep going until what? We have 4, 9, 4, 42, 102, dot, dot, dot. Right. Now, is 42 and 102, are those out of order? Nope, so you'd end up stopping, right? You're describing an algorithm called bubble sort. And what you're doing is you're swapping these two, swapping these two, swapping these two. What you would actually do after this? You've still got 34 over here, 12, 2, and 0. So what happens is you continue to look at pairs. 42 and 102, they're in order, so leave them alone. Move on to this other pair here where you see that 34 and 102 are out of order. You do the same thing with 102 and 12, 102 and 2, and 102 and 0. At the end of going through this array one time, what have you done? You've taken 102 and you've shoved it all the way to the end. You've bubbled it up to the end. And that's why it's called bubble sort. All right? That's one way. Good. Is there another way? Think about you being a human here. How would you actually do it? If I threw all of these on the floor, what would you do? Okay, find the smallest one. In this case, what is it? 0. How did we go about doing that? We started at the beginning. Okay, 42. Well, that's the smallest thing I've seen so far because that's the first thing I've seen. 4 is even smaller. Okay, that's the smallest thing I've seen so far. You look at 9. Right? 9 is not smaller. 4, that's equal, so it's not technically smaller. 102, 34, 12, 2. Oh, 2, that's even smaller. So update the smallest that I've seen so far. Then you look at the last one and you see, oh, that's even smaller. At the end of that, you found the smallest element. Now what do you do with it? You swap it with the first element. Right? That leaves you with, and I'll go ahead and edit this to be what was it again? A 0 and 42. Once I swap them, 0 and 42. There we go. After I've swapped them. Okay. Continue. Should I start at the beginning though? If I go through and find the next smallest element, what would I end up doing? 0? Okay, the 0 is the smallest element I've found so far. You go through the rest of it, you find nothing smaller. So what do you end up doing with 0? You end up swapping it with itself? Nope. Don't start at the beginning. Where should I start now? Index 1, the next index. Go through 4, 9, 4. 4 is the smallest element so far. Not smaller, not smaller, not smaller, not smaller, not smaller. Found something smaller. Continue to 42 to see that it's not smaller. And you found that 4 and 2 need to be swapped. Right? So 4 and 2. Okay? Where do you go next? The third one. Find the next smallest element, swap it with that element. Continue doing that until the end. Right? In general, what would it look like? There we go. So there's A1, or A0, excuse me. A2, or, okay. 1, A2, dot, 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 AI minus 1. At some point, you're looking at A sub I. And you, everything that you've done up to this point is sorted. Right? This is the current value, current index, I. What you need to do is you need to look through all the remaining values. A1, you assume that this is the minimum. And then you go through the rest of the values, AI plus 1, AI plus 2, dot, 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 all the way up to n minus 1. You find the minimum, and once you've found the minimum, suppose that it's right here, right, what do? You swap it. Okay? What am I doing each and every single time? I'm finding the minimum, I'm selecting the minimum, and that's why it's called selection sort. This is the one that we'll actually go ahead and implement. You can go ahead and implement bubble sort if you want to. At the end of the day, we're not going to use any of this stuff because they're all terrible. Right? So let's go ahead and implement selection sort. All right, so selection sort is going to take an array, const int star array, or A. Right? Now, am I going to be I'm going to ask the same question before. Am I going to be making changes to the array? If I swap something, isn't that a change? Right? So should I make it into a const? Probably not. If you're going to be making changes to the array, then it can't be const. Now you can come up with a different version where, here you go, here's an array selection sort. Go ahead and make a deep copy, then sort it, and give me the new copy so that I have both the original and the sorted version. Right? And you can do that if you want. I'm not going to, though. Instead, I'm just going to simply return nothing. You give me the array, I manipulate it, change it, and it is now sorted, and I don't give you anything back. Okay? So help me out here. What kind of a loop do you want to do now? A while loop? Probably not. You're going to run for I running from some starting point. I is less than some ending point. I plus plus. Let's outline this. Find the minimum element among elements a sub, as the picture suggested over here, a sub I through a sub n minus 1. A sub I through a sub n minus 1. Okay? So how do I go about doing that? Another for loop. Can I reuse the same index variable? Nope. I mean, I can, but then it won't compile, right? So I'll go ahead and go with J. That's the next one. Where should I start? Should I start at a sub I? Well, I need to find a minimum index, right? So int index of min, right? Where should I start that out? Should I start it all the way back over here at the beginning? Nope. Think about it in the middle of the algorithm, where I'm at everything up to this point has been sorted already. Ignore it. Don't touch it. It's done. So look at the remaining elements, I through n minus 1, and find the minimum. So how do I start out? By assuming that a sub I is the minimum. In other words, the index of the minimum is I. Now, I'll run j from I plus 1. Why don't I include I there? Because I'm going to start here and assume that this is the minimum until I find something to the contrary over here. J is less than n because I want to go all the way to the end, right? I want to go all the way to the end, and so it's strictly less than n will give me that. Okay? J plus plus. There we go. If you find something that is less in the array, index of min is less than, j is less than a sub index of min. If you find something, a sub j, that is less than what you found so far, then simply update your min index. Index of min is equal to j. At the end of this loop, you've found the minimum element, right? So I swap them. Swap what, though? The picture. Suppose that it was j, a sub j. Which ones am I going to swap? It's not j. Undo that. There we go. A sub min index. There we go. So what am I going to swap? A sub I and whatever that min index is. How do I swap? Is there a swap function? We wrote one, right? Remember? So if you want to bring that in, you can. But it's not that big of a deal. All you have to do is what? Int temp is equal to the array of index of min. That frees up the index of min to be given the value a sub I, and that frees up a sub I to be given the value of index of min. Excellent. Now let's come back up here and think about where I should start. Where did I start the entire process to begin with in this particular example over here? I started at index what? 0. So 0. What do I go up to? So again, think about this general kind of in the middle of the algorithm kind of thing. Suppose A0 through A sub n minus 2 are all sorted. What can you tell me about this last element, A sub n minus 1? If everything's already sorted over here, what about this last element? It's already sorted, right? Well, sorted and not sorted, but you've already selected the n minus 1 the smallest elements and put them all over here. What can you tell me about this element right here? That's going to be the maximum, right? Or maximal. So do I need to move it? What if I did? Find the minimum among one element. What's the minimum among one element? That element. Swap that element with that element. Is there any point in doing that? Nope. So we'll go ahead and stop short. N minus 1. Now, actually, we go up to n minus 2, but because this is strictly less than, we don't have to worry about that, right? Okay. So selection sort, I'm going to go ahead and move that over. Oh, I'm going to go ahead and add that as a prototype over here. And let's test it out and make sure that it works. So remember that the binary search was not working on this numbers because it was unsorted. Let's go ahead and sort it now. Selection sort, numbers, and pass in the size here. If it's sorted, we should see that this binary search is now going to work. Oops. Did I not? Oh no. Selection sort, numbers. I saved it, right? Maybe I didn't save this stuff. Save. Save. GCC. Nope. Okay, good. This gives us an opportunity to debug. Anybody see what I did wrong? Oh, somebody has a suggestion? No? Okay. No suggestions online, so let me just go ahead and take a really quick look here. J, index of min, I. I should put this here, but that's not going to matter. I don't see index of min. J, you find something that is less than index of min. Okay. Sorry, line 10 or? No, line 84. 84. Oh, thank you. So I'm taking index of min and I'm putting it into temp, right? Here's temp over here, right? And then that frees up index of min to take on the value I. And then the value of I, what do I do with it? I just overwrite it instead of taking in temp. Thank you. I was hoping that we could fire up GDB and take a look at what was going on, but there, that fixed it. All right, sorry, thank you. Excellent. All right. Let's see. Yep, good job online. You're on a 20-second delay though, so we got it in here first. All right. So that's selection sort. How good or how bad is it? Right? So we're not going to go through a full analysis. Actually, we could go through a full analysis if we really wanted to, but let's go ahead and just take a look at those two for loops. This for loop executes how many times? Goes 0, 1, 2, 3, 4, all the way up to and including n minus 2, right? Okay. So the outer for loop executes n minus 2, that is a 2, times. Right? What about that inner for loop? How many times does it execute? Well, it executes for I plus 1, I plus 2, I plus 3, all the way up to n minus 1. So it executes I plus 1, I plus 2, I plus 3, ... up to n minus 1. How many is that with respect to n and I? N minus 1 minus I. Right? So n minus I minus 1. I'm just rearranging those. Okay? Don't worry about it. Let's just go ahead. What should I do with these, by the way? I'm going to multiply these together. Why? Because the outer loop executes, the inner loop executes each and every single time. It goes through its entire loop structure for each iteration of the outer loop. Right? So it's something like this, right? And ... However, we can come up with a formal analysis, a full summation if you really want to. But at the end of the day, what is going to be the value out front if I multiply these two together? N times n plus, and then a bunch of other stuff. Right? So it's approximately equal to n squared. Right? So did we look? We looked at binary search, right? And that it was logarithmic. Yes, last time. Remind me. Okay. We also looked at linear search, how it was linear. Pull all three of these things together. Oops, that's not what I want. we go. All right. So what does n look like for linear search? Looks something like that. This is linear search. What does binary search look like? Something like this. Oh, I didn't want that. Something like this. This is logarithm for binary search. What about n squared? What does that look like? Looks like that on this scale, right? N squared. And this is going to be selection sort. All right? So, how bad is that? From the perspective of linear search, remember when we went from n to, say, 2n, right? Then the number of comparisons in linear search doubled. What happened for binary search? If we went from 1 million to 2 million for linear search, we would end up doing 1 million more comparisons. But if you go from log n to log 2n, you double the input size. What does that equal to? Log of n, pull out your log identities, right? Log of AB is equal to what? Log of A plus log B, right? So, applying that identity here, what do we get? Log base 2 of 2, which is equal to what? 1. In other words, you only do one more comparison. One more. Now, let's look at this with respect to selection sort. If I go from n squared to 2n squared, what do I get? 4n squared. This is 4 times as much work. Now that might not seem all that bad, but remember the demonstration I gave you yesterday, or on Tuesday, where we estimated that it would take an hour and a half or 40 minutes or whatever it was to actually execute that program. That was because it is a quadratic algorithm just like this one is. It's going to be n squared. This one was log n, and then linear, of course, was just n. Right? These things matter, right? Especially as the input size grows. Right? Even for moderately sized inputs of, say, 100,000, 1 million integers, n squared is not acceptable at all. Right? So let me show you a different algorithm. All right? Let's go with the same example here. This is an unsorted array. And what I'm going to do is I'm going to show you a different algorithm. We're not going to program it, and we're not even going to analyze it fully. I'm just going to show you that there are better alternatives out there. What we're going to do is we're going to start at this element right here. This element is going to end up being what's called a pivot. So what is a pivot? No? Basketball, what's a pivot? Pivot foot. Oh, no. Okay, no basketball. I don't know of anything else. I mean, farming implements will have pivots, right? It's ground. It's in the ground, and then you've got irrigation that goes around that central location, right? It pivots around it, right? So what is a pivot? It's a point at which things rotate around it. Your pivot foot in basketball is the pivot is the once you've taken the control of the ball and stopped, right? The first foot that you put down is your pivot foot. You can move around that pivot foot, but you can't bring it back up, right? It's an anchor. What we're going to do is we're going to pivot elements around this element. So we're going to look at, say, 4. 4 is less than 42, so what we're going to do is we're going to shove it to the left. 4. 9 is less than 42, so we're going to also shove it to the left. Shove it to the left, 102, that's greater than 42, so I'm going to shove it to the right. 102. I'm just showing you this conceptually here. 34, 12, 2, and 0 are all less than 42. Now I've pivoted everything that is less than 42 over here, everything that is greater than 42 over here. So where does 42 belong now? Right between those two areas, right? And at that point, 42 is where it belongs. Don't move it. But you have this array, and you have this array over here. Why a circle? There we go. That's as good as it will get, right? 102. Tell me about that array containing 102, that sub-array containing 102. Do we need to sort it anymore? No, why? It's of size 1. By definition, an array of size 1 is sorted. We do, however, still need to work on this one over here. So how do we go about doing that? We recurse. We call our quicksort algorithm, this is called quicksort. Why do you think it's called quicksort? It's quick, right? So all we're going to do is recurse on this one, but when we recurse on this one, we see that it's only of size 1 and there's nothing to do. But otherwise, we'll recurse on this one and we'll repeat the same operations. You choose this as a pivot, and then you move stuff around. 9 is greater, so it gets shoved over here. 4 is equal. You can break ties arbitrarily, go left or right, just be consistent about it. 4. 34. 12. 2. And 0. And now where does 4 go? Right in the middle. It's done. Don't touch it anymore. Recurse on this subarray. Recurse on this subarray. And continue until everything ends up being sorted. Quicksort. Now, we're not going to analyze it, but quicksort has a best case and an average case slash average case. Running time of n log n, right? This is the number of comparisons. Much, much, much better. In fact, let's go back to our graph here. Where would you put n log n? Would you put it between, would you sandwich it between n and log n? Remember, it's n times log n. So, is it bigger or smaller than n? Bigger, all right. But is it bigger or smaller than n squared? Definitely smaller. So it would actually look something like this. Right? It's going to be a little slightly higher than this, but this is going to end up being n log n. In fact, we have a name for this. It's called quasi-linear. It's almost a linear function, right? This logarithm factor over here, they're so small and inconsequential when you take n as n tends towards infinity that it really doesn't matter. You could treat these for all practical purposes, for all practical inputs, as the same thing. Right? But it is n log n. Way, way better than n squared. Let's look at it from this perspective. If it's n log n and I double it, right? This is quicksort. What's it going to look like? 2n, or sorry. If I have n log n and I double the input size, I go to 2n log n, log 2n. What does that equal to? 2n times, and then what happened to that log 2n with our log identities? Log n plus 1. Right. Go ahead and ignore this lower order term here. And what do you have? 2n log n. That's why we call it quasi-linear. Because if you did this with, say, a linear search, it just doubles. And it also doubles here. It goes from n log n to 2n log n, again, ignoring this lower order term here. Right? So that's why it's quasi-linear. Right? And it is much, much better, even in practice. Right? So all that's left here is to actually program it. I don't want to do that though, right? I want to actually sort stuff properly, right? To do that, I'm going to go ahead and bring in the standard library, which is already up here, by the way. The standard library has this function called qsort. What do you think it is? Quicksort, exactly. There's no such thing as a built-in selection sort. There's no such thing as a built-in bubble sort. Those are terrible algorithms. They're good for illustrating algorithms and algorithmic approaches and strategies and stuff like that. They are terrible in practice because they are very, very inefficient. Quicksort, however, is pretty quick. Right? So how do I go about sorting this? Well, I'm going to go ahead and pass in numbers here. Right? Numbers could have been a double array, though. Numbers could have been a film array. Numbers could have been a student array. Right? So do you think I have a quicksort for integers, a quicksort for doubles, a quicksort for films? Think that's a good strategy? That's not what they do. There's only one quicksort. There's one version to rule them all. So how does it know how to sort it? Right? Well, quicksort knows how to sort things. It just doesn't know how to order things. I have to give it some more information. So let's go ahead and visualize this. And right there. Okay. Oops. There we go. All right, so this is the quick sorting algorithm, qsort, say. It knows how to sort. It just doesn't know what it's sorting. It doesn't know that it's integers. It doesn't know that it's doubles. It doesn't know that it's films. And consequently, since it doesn't know what it's sorting, it needs another piece of the puzzle here called a comparator. Now, quicksort and selection sort, whatever else, they know that, okay, well, if you told it that these two things are out of order, it knows that it needs to swap them. If you told it that this thing was less than your pivot element, then it knows that it needs to put it on the left side. If you said that this thing is greater than your pivot element, it knows that it needs to put it on that side. It just doesn't know anything about these things that I'm holding in my hand, A and B. But a comparator does. So what the sorting algorithm does is it hands off A and B to this comparator. The comparator knows that they're integers. The comparator knows that they are doubles. The comparator knows that they are films. Right? And it knows how to compare them. How do you compare a film or a student? First name, last name, NUID, whatever, right? It knows how to order them. And ultimately, what it returns back to the sorting algorithm here is an integer value. It will return something negative if they're in order, A, B. A comes before B, B comes after A. It'll return 0 if they're the same thing from the perspective of the sorting algorithm. It'll return something positive if they're out of order and need to be swapped. Right? Otherwise, they're in order, negative, and it doesn't need to do anything with them. Leave them as they are. It's 0. Okay, well, break ties however you're going to do, break ties sorting algorithm. Right? That way, we only need one sorting algorithm, qsort, to sort anything that you want. All we need to do is come up with an array of integers and then create an appropriate comparator to give to the sorting algorithm as well. Where have we seen this before? Where have we seen this pattern right here? I can give you two things, and then it returns something negative, positive, or 0, depending on the relative order of those things. Haven't we seen something like that before? What if I said apples and bananas? Right? You give that off to what function? It's a string, so string str CMP for comparisons, right? And it returns something negative, positive, or 0, depending on the relative order of those strings. Now we're going to have to write our own comparators here, okay? So let's talk about that. Sorting in here we go. Select, okay, that's an older comment. So, searching and sorting in practice. Right. So in general, You do not write your own searching/sorting algorithms. You use one built-in generic sorting or searching algorithm. Function/method, if you're talking about Java. All right. However, the built-in functionality is generic. So it doesn't know how to what the elements are. It doesn't know what the elements are or how to compare them. Thus, you also need to define a comparator function, and this will be in C, or a comparator in Java. So, I don't know that if you looked it up in the dictionary, I don't know if there would be such a thing as a comparator, right? OR, maybe comparator, maybe. But it's a computer science thing. Maybe it is a real world word. I just don't know it, right? But that's what we need to give to quicksort, or that's what we need to give to any algorithm that you want to remain generic. Okay. What is a comparator? Comparators in C. Right? In C, a comparator function is a function that compares two generic elements and returns the following. It returns something negative if A comes before B. Oops. There we go. It compares two generic elements, and I'll give them names here, A and B, and returns something negative if A comes before B. It returns something positive if B comes before A, or switch those around, and A comes after B, however you want to put it, and 0 if it is equal to B. Comparators in C always have the same signature. In C, the signature of a comparator function must be as follows. Right? Int CMP const void star A, const void star B. It takes two elements, A and B. Right? So why does it return an integer, by the way? Again, that's the contract, right? It returns something negative, something positive, or something zero. Or something zero, right? It returns an integer. It has to return an integer. And it takes two arguments. Both of those arguments are const. Both use const. And so are unchangeable. Right? Both are generic void pointers. Where have we seen that before? Void star. Where it doesn't matter what it's pointing to, right? So it could be pointing to an integer, int star. It could be pointing to a double star. It could be pointing to a char star. What returns a void pointer, a generic void pointer that you've used before? No? Do you have a malloc for integers? Do you have a malloc for doubles? Do you have a malloc for films? Nope, you have one malloc that returns what? A generic void pointer. And then you can you can go ahead and put out front that typecast to force it to become an integer pointer, to force it to become a double pointer, or to force it to become a character pointer. Right? And same thing here. If I want this to be generic, I have to use generic pointers. Sometimes it can be pointing to an integer. Sometimes it can be pointing to a double, etc. Now, inside the function, you follow a general pattern. One is you cast the generic void pointers as the actual types that you are comparing, because the comparator does need to know something about the values, right? Then you set up a if else statement to return 0, something negative, 0, or something positive, depending on the relative ordering of your arguments. All right? So what I want to do as an exercise now, with the remainder of our time, is go ahead and use this exercise. Write a comparator function for integers that orders them ... how. So given a bunch of integers, what order could you put them in? What order have we been putting them in? In increasing order. What's an alternative? In decreasing order. So let's go ahead and go with increasing order first. In increasing order. ... Okay. Let's come back over here. Let's go ahead and go into my search.c. And let's go ahead and create a comparator for integers that goes in ascending order, non-decreasing order. Int CMP, int A, int B. Is that a comparator? No. What does a comparator have to have? It has to have this signature right here. Okay? So it can't take integers. It has to take int star pointers. It can't take integer pointers either. What kind of pointers does it take? Void pointers. Void star B. Okay? Now, is that enough to be a comparator? What else do you need? A guarantee that you're not going to change it. Const. Const and const. That's a comparator. That's the only thing that's a comparator. And by the way, you should be more descriptive here. It's a comparator for what? For integers. Okay. The first step here is we're going to cast the generic void pointers to the actual types that we're going to be comparing so that we can actually, reason about them, right? If I did something like this, if A is less than B, then do something. Is this going to work? What is A? It's a memory address. What is B? It's a memory address. Sure, you can compare that memory address to that memory address. That would be like you having two strings. Hello is equal to hello. Right? Can you do that with strings in either language? Nope. Right? You can, and it'll compile and it'll run, but it's not going to give you true in this case. Right? Instead, what do we need to do? We need to cast them first. So cast the generic void pointers as integer pointers. So I'm going to go ahead and retain my promise that it's going to be const. And here's my integer pointer, and I'll call it x, is equal to const int star A. And same thing, but for B. And now I've got x and y. Now, x and y are integer pointers, and you can reason about them. You can say that whatever's stored in that memory location, treat it as a 32-bit integer. Whatever's stored in that memory location, treat it as a 32-bit integer. Now you can make your comparisons back and forth. Right? Is this how I do it? If x is less than y, then return something. Can I compare x to y now? They're still pointers. So how do I take a pointer and make it into not a pointer? Dereference it with the star operator. Dereference it with the star operator. Right? So x comes before y. If this is an ascending order, 2 and 5, because I don't have enough fingers. Right? They are in order, right? What should I return? Are they the same? 2 is equal to 5? Nope. Remember the contract. That it returns something negative if A comes before B. It returns 0 if A is equal to B. 5 is equal to 5, or 2 is equal to 2. It returns something positive if they're out of order, right? 2 and 5. So if A is strictly less than Y, I should return something negative. That something can be -1. else if x is greater than y, they are out of order, and what should I return now? So return something positive. I could go ahead and do something squirrely like this, and 42. That's my favorite number. Right? Why? Just don't do weird stuff like that. Else, what is the only other condition here? They're equal, so return 0. There we go. Excellent. That's our first comparator. Let's go ahead and use it. I'm going to come back over here. I've got to make sure that this is in the header file. And now we can come back over here to demo. And how do we use it? So quicksort, we'll talk more in detail about this next week, but it's going to take actually 4 arguments. It needs to know a lot of things. It needs to know the array that you want to sort, how big the array is, in other words, how many elements are in the array, but also it doesn't know anything about the elements that are in the array. This could be a 32-bit integer and this could be a 32-bit integer. And swapping them means taking this 32 bits and this 32 bits and moving them. It could be that they are 64-bit doubles, 64-bit doubles, and he needs to take 64 bits and 64 bits and swap those. Right? It could be that they're films or students and they're 40 bytes and 40 bytes, and it needs to take these 40 bytes and swap swap it with these 40 bytes. So how do I tell quicksort how many bytes each thing takes? Size of, our old friend size of, and then provide the actual type. Right? Now it knows, oh, size of, that's 4 bytes, that's 4 bytes. I know how to move 4 bytes. I don't care what's stored in those 4 bytes. I know how to take these 4 bytes and these 4 bytes, and I know how to move them. Right? The last thing that you give it is the comparator that you want to use. So this is weird. How do I give a function as an input to another function? So this is something that we'll cover next week with in more detail. It's going to be function pointers. So remind me, what are pointers? Pointers can point to an integer. It can point to a double. It can point to a string, right, a character. In other words, a pointer can point to an element that is stored in memory. Well, what else is stored in memory? Arrays. And a pointer points to the first element in an array, right? And there are 5 elements in that array or something. Right? What else is stored in memory? Your code, right? So you could have a pointer pointing to your code, right? You can have a pointer that is pointing to your function, right? Main. You've done this before in GDB, right? Break at main. Well, how does it know where main is? Main has to be stored in memory somewhere, right? And so you can have a function pointer that points to a function. The way that we're going to do this just for now is by the function name. CMP int is what I called it. It is not a function call. Putting parentheses around this means you want to call that function, invoke that function, and take its value and do something with it. But the name itself is its pointer. Hand off this function to that function so that it can use it as what's called a callback. Okay. Let's go ahead and compile this and see that it actually still works. A.out. You can see that my binary search still works even though I'm using quicksort now instead of my selection sort. Right. Just to show you a little bit of contrast before we leave for the weekend, let's make one more comparator, but instead of ascending, we're going to go ahead and make it into a descending. Okay? So, come back over here. What does a comparator look like? Oh, exact same thing as before. Now this one is going to be descending. Right. What do I change out of this? I still have to cast them as integer pointers. Right. But now I want descending. In other words, I want 5 and then 2. This is in order now. Right. 5 comes before 2. So what should I do? Return something positive, right? 5 and 2, they're out of order. I need to put them in order, so something negative. Right? Lots of copy pasta just to do that. Is there a better way? If I already have a comparator for integers in ascending order, how could I reverse it? Let's get rid of all this. What if I called this function?
Call it in reverse.
All right, so call it on A and B. That's going to be some value, right? All I did was take positive 1 and make it negative 1. Take negative 1, made it positive 1. 0 stayed the same. So what could I do with that value there? Negative 1 times. Right? Return. And all it's doing is reversing everything. So you might have heard of code golf before. Has anybody heard of code golf? So here's a snippet of code that does some piece of functionality. Can you come up with a smaller piece of code that does the same exact functionality? It's kind of like golf, right? The lowest score wins. The lowest number of strokes wins. So can we get this down even further? Can we code golf this? There's only one line right now, right? Before it was like 10 lines. Now we got it down to 1 line. Can you get it down to a fewer number of characters? What if I don't multiply it by negative 1? What if I just simply swapped the arguments? Right? Now I've got it down. That's as simple as you can get. Right? Let's go ahead and see this in action. I will go ahead and call quicksort after this is all said and done. I'll go ahead and call quicksort again, but instead of passing it this comparator, I'll go ahead and go with a descending comparator. And let's go ahead and print everything out. So for int I equals 0, I is less than n, I plus plus. Printf array, or what was this called? Numbers. Sub %d is equal to %d and the line. And then, forget about it. Let's just do it in one big giant line. And numbers sub I. There we go. Right. And you see that it's in descending order now. Right? Before, it was in ascending order using this one comparator. Now, it's using a completely different comparator, but everything else was the same. I called quicksort. I reused the same algorithm. Reused the same array, the same size and the same number of bytes for each element. I just had to plug in a different comparator, and I got completely different behavior. Right? Use the same quicksort for doubles, ascending, descending. Use the same quicksort for for students, based on last name, based on a combination of last name, first name, based on based on say NUID, based on GPA. If you want to sort your roster according to GPA top to bottom, right? You can create a comparator for that. If you've got a student with 4 pieces of data in it, then there are 8 different ways of sorting them. In fact, more than that, right? You can sort it on 1 piece of data and ascending or descending. There are at least 8 different ways of doing that. Do you want to write 8 quicksort algorithms? 8 selection sort algorithms? No. You use what's built in and you write 8 different comparators instead. All right, questions on that so far? No? How do you do it in Java? So, comparators in Java. I don't have a Java thing open right now, so we'll just do this in code mode right here. All right. So in Java, it's an actual class, and this is just a preview. We'll go over it in detail next week. But you create a comparator for, say that you've got a list of integers, numbers, right, is equal to ... Right? You want to create a comparator, but if you want to sort a list of integers, do you want a comparator for doubles? Probably not. If you're sorting a list of integers, do you want a comparator for students? Probably not. You want a comparator for integers. Right? If you're sorting an array or a collection or a list of something, you have to have a compatible comparator for that something. Right? This is a comparator for integers, and I'll just call it CMP int, just like I did before, right? Is equal to new comparator for integers. And here's some brand new syntax. This is what's called an anonymous inline class, right? What I'm doing is I'm creating a brand new class without giving it a name. I could put this comparator, this functionality into a class called my awesome integer comparator that sorts in ascending order, right? Very, very long name, but it's descriptive, right? How many of those are you going to need? A comparator that sorts in ascending order. Do you need 2 of those? Do you need 3 of them? Do you need 50 of those things? No. So don't make a class where you can churn out copies of it. Just create it inline and create 1 copy. You don't need to have this fancy name, my awesome comparator for integers that what sorts in ascending order, right? You don't need a name at all. And there is no name here, right? It's just a generic comparator. You'll note here that it opens with a curly bracket, ends with a curly bracket, and then a semicolon at the end here. Inside that, that's where we put the class definition. The only thing that is defined by a comparator is this compare2 function. So public int compare compare, sorry. And then int integer A, integer B. Okay, no questions still. Yeah, it goes in between the 2 curly brackets here, right? So let me go ahead and, that's not what I wanted. Expand this out so you can see it. Yep. This function right here is going to go inside of the definition of this class. Think of it as, you could put it over into its own class called myAwesomeComparator, right? A public class myAwesomeComparator, and then it would have opening and closing curly brackets, inside of which you would put all the functions. And I'm just doing that here, but not giving it any name. That's why it's anonymous, right? So comparators in Java are typically, you define an anonymous class, inline class. And that's what this is doing. There's no name to it, so it's anonymous. I can't call it, I could call it my awesome comparator, but I'm not going to call it because I don't need more than one of them, right? I don't need the first instance of my awesome comparator, the second instance of my awesome comparator, the third instance of my awesome comparator. I just need one of them. And so if there's only one, you don't need to name it my awesome comparator. Now what do you do inside this function? Exactly what you did with the comparator in C. If A is less than B, return something negative. Else if A is greater than B, return something positive. Else return 0. And there are shortcuts to this as well because an integer is a built-in class. An integer is already comparable. You don't need to do this, right? You can just do return a.compare to B. Right? What about reversing it? A compare to B, how do I reverse it? B compare to A. Right? Or multiply by -1. Lots of different ways that you could do this. You don't need to be explicit about this if it's already built into the language though. Okay. We'll talk about how to use a comparator and hand it off to another sorting function. Basically, that if you've got a list there above, then it would be collections.sort numbers, and then you give it the comparator, comp int. Right? That's it. It's different than C because C we use function pointers. In Java, there are no pointers, so we have to use a full anonymous class like this. That's a little bit of a preview. We will go into more detail next time. Okay? All right. I will have a good weekend.